First of all, thank you very much for having me. I'm going to move quite quickly. 15 minutes is not a lot of time, so very easy to fill. Obviously, with Autodesk, we're a commercial organisation, a software provider, providing tools into industry, but we've also been involved in a number of research projects, so have experience, whether that's sort of powder bed, additive, right the way through to DED, etc., on both research projects and on commercial implications there. I'm going to talk to you today specifically about generative design, and we're going to look at 3 case studies for generative design. And I think there's a few themes that run through this that pretty much impact design for additive manufacture in general, and that is that demand is increasing significantly. That's both demand in terms of a scale, but also in terms of customization, with the desire to do that with less natural materials and less resources available, and we have this opportunity to do things better than we currently do. And that's really driven by sort of 3 areas. One is that the things that we're making are different, and this is about connected devices with multiple materials, etc. So things are no longer mechanical or electrical, they're often both. Then the way that we make them, so we're being exposed to new material, new technologies, etc. And then finally, never has that been more prevalent than during this COVID pandemic, the way that we work is very different. So we are often working remotely, we have global supply chains, etc. So we're going to talk a little bit about generative design. And first of all, we'll just talk about what that actually is. Now, it's interesting here that we're talking about design for additive manufacture in this consortium. And really, generative design is about an algorithm that tries to automate the design process. So I think it's very interesting to think about it in the context of what are some of the considerations that the algorithm uses that human designers should also be considering or using for their design process. And the first thing to think about is what is the difference between generative design and topology optimization. And I'm obviously oversimplifying this, but in its most simple state, topology optimization is about taking an existing design and either removing or adding material to that to make it lighter or stronger to meet the desired outcome. Whereas if we look at this analogy here, generative design, for a start, you actually start with no design at all. You start with a load case or a specification or a set of objectives. So generative design is an AI algorithm that automates the creation of hundreds or even thousands of designs, whilst also considering other variables. So what manufacturing processes do you have available to you? Is this something that's going to have to be subtractively machined, for example? If so, is that done in 3-axis, or do you have 5-axis capabilities? Is it going to be 3D printed? Does it need to be castable, etc.? And then you take those designs and filter them down based on your key criteria. So is it weight that's important, time to manufacture, overall cost, etc. So you filter those designs down and then ultimately can work with a few of the key designs to come out with an outcome. And those are kind of some of the key differences between traditional topology optimization and generative. Moving into just looking at a couple of case studies for this. The first of all is with a company called Lightning Motorcycles. So they came to us asking us to, how would we go about designing a swing arm for the rear of the motorbike? Now, if we think about this in the traditional sense of designing a component for an industrial application, what tends to happen is a designer will go away, think about sort of several design concepts, and then you have this iterative process where they will assess them based on manufacturability, based on other criteria such as cost, etc. You'll go back through this design loop where there'll be design iterations, etc. Finally, you'll have a validated design that is manufacturable and that can move on to the production stages. Now, how things differ with generative is that it produces, because it's considering this idea of manufacturability and the various design constraints, and it produces hundreds or even thousands of already validated designs. So any one of those designs could be taken at any point and simply taken onto production, if you like. The idea of this, or the benefit to this, is that it significantly reduces or increases productivity, if you like, reduces time to market or time to production. So if we look at that specifically with this motorbike example, how would it work? Well, we have the main geometry. We can set geometry that we want to preserve. So this may be mating faces or critical areas. You've then got geometry that you need to avoid. So, for example, you don't want a part that's going to go straight through the rear tyre. We set load cases, so these are the loads that we need it to endure, and also the manufacturing capabilities that we have available, whether that's 3D printing or traditional manufacturing techniques, etc. We can then produce lots and lots of designs and then start to filter those designs based on criteria. That could be cost, that could be time to manufacture, that could be strength, weight, etc. Filter that down to a smaller number, and then we can look at a smaller number of designs and further refine them. Now, ultimately, it may just come down to aesthetics. You may like one design more than the other. And as we sort of talked about in a few of the previous presentations as well, you then have this concept of the post-manufacturing operation. So very rarely do we take things out of the printer and they're simply good to go. So you need to do the path planning of actually creating the tooling or tool paths to generate the 3D print files. But then you also need the additional post-finishing operations. So for example, if you want to create a hole in something, is the best way to create that hole a subsequent operation, i.e. machining or drilling, or is it to print that hole? Now, largely, if you want an accurate hole, then printing it is going to be quite a bad idea. You almost definitely want to machine that afterwards. And depending on how accurate the hole needs to be, you consider whether that's going to be drilled or bored, or you have various options available to you. Likewise, if you need a mating face, for example, you know that you're going to need a subsequent operation to actually machine or subtractively remove material from that face. So you'll probably want to add a little bit of material onto that face ready for the subsequent machining operations. You have all sorts of post-finishing operations such as wire EDM and so on. So this is the sort of finished part, and you can see it on the Lightning motorbike, and you just get an idea of how, or some of the design considerations that went into that when it was being produced. The next case study we'll look at is one from GM. So GM are obviously, and the automotive industry more generally, are no sort of stranger to design innovation. It's quite a nice case study because of its simplicity in the part that we're looking at. So you have effectively a set of components or an assembly that holds in the seatbelt buckles. So in terms of the job that it has to do, it's quite easy to define. So it needs to be able to obviously mate or interact with these standard components. It needs to be able to sustain these sort of forces and so on. And here are the various design constraints. So with Generative, you can obviously input those load cases, define the manufacturing that you have available to you, and then Generative will go away and produce lots and lots of designs, and we can then start to narrow that down based on the key criteria and ultimately settle on a design that we want to work with. Now, one of the key things here is that we ultimately took an assembly of, I haven't counted them, but let's say there's half a dozen different parts. So you would have the manufacturing of half a dozen different parts. You would have then the assembly of that set of parts. And we've taken that down to a single part, so one piece construction. We've also reduced the weight of this and increased the strength of it. So the weight implications are interesting because they not only imply that there is less material used in the production of the part itself, but also when you think about from a vehicle perspective, if you lower the weight of the component, that's less weight for the vehicle to be trailing around for the rest of its life, and that has implications on the amount of resources being used for that and so on. So here we see the additively designed or generatively designed component, and then we see the original and how that compares in terms of its simplicity. Now, this one I think is quite an interesting one because it usually sparks a debate and highlights the cynics in the audience, because it's very easy to be cynical with this stuff and say, oh yeah, but it may be lighter and it may be more simplistic in that it's a single component, but how much did this one cost? How long did it take to manufacture, etc.? And absolutely, those are completely valid, correct concerns in that this one was significantly more expensive to produce. The automotive industry is generally incredibly lean, and so it would have taken also significantly longer to produce. But the point is that it's more of an indicator of the direction of intent or the direction of the industry, because I don't think there are many people that look at these technologies and feel that they are going to get more expensive, slower, more difficult to access. And so as I say, these things will ultimately open up, democratize, and become more and more mainstream and overcome the hurdles. And it's just a nice indicator of intent. The final case study that I'm going to look at is this piece that we did in collaboration with NASA. So this is an interplanetary lander. The idea is that it can take a payload and head off to different planets or moons of different planets and so on within the solar system. So it's quite a nice case study. Now, some of the interesting things here, and again, I think are really quite relevant from a design for additive manufacture perspective. If we take the two main components, we've got the body of the craft, and then we have the legs of the craft. Now, if we look at the body of this, it's most people look at this and automatically assume that this was additively manufactured. It wasn't. It was sand cast. So there's a few interesting points about that. So the first thing is that additive manufacturing, particularly in the aerospace industry, you have difficulty improving out the process and repeatability, etc. And there is a natural aversion to these things because of the unknown. Effectively, additive manufacture opens yourself up, particularly with metal additive, to lack of fusion defects, voids within the material, etc. So if you can bypass some of that and use traditional manufacturing techniques, so casting, for example, has been around for thousands of years. If you can use traditional manufacturing techniques, it bypasses some of the steps of the approval processes when you're going through some of the testing. But that's not to say that additive manufacture doesn't have any role to play in the production of this. As you can see by the shape of it, it's very, very organic. And where additive manufacture is relevant here is and where it is very important more generally in industry is not necessarily just making the parts or the components, but making the parts that make the parts. So my background is one of tool making, and quite often, many of the things that we look at, or many of the components, products that we have, they were never simply just designed and made as the component, if you like. You have the overall component that you want to end up with, and then you design and make all of the necessary tooling required to make that component. So in this example, 3D printing or additive manufacture was used to print the pattern that was then going into sand mold, and then also used to actually print some of the sand for the casting process. So to present some of the cavity and core halves for that sand casting. So additive manufacturing has a very significant role to play in the production of this part, even if the part itself wasn't additively manufactured. You then have the added benefit brought in there that when it comes from a testing and analysis standpoint, this part was cast, which is a known technology and more easy to get through certain approvals. So here you see the sand casting as it's being broken out of the mold for the actual part. Then the final piece is the legs again. They look very organic in shape. If we think about the design constraints or the manufacturing constraints that we can apply to generative design, these were actually constrained so that they could be manufacturable using 5-axis machining. So there wasn't necessarily a additive manufacturing element to these, but again, you can see where it could be very, very relevant and a huge implication for it in commercial applications and industry. Is if we look at machining this part, we're actually fortunate because if we have these very easy blocks on the end that make work holding quite simplistic. But at some point, we're going to need to machine these blocks off the end and then machine where that material was. So you have this very complex organic shape. How do you hold that part? When it comes to subtractive manufacture, that's a great example of an area where fixturing often makes up a significant cost of any project. So both designing and manufacturing fixturing to hold these parts whilst you machine them, it has some very serious implications to both time, cost of the project as a whole. Additive manufacturing again steps in here because it's very sort of well fitted, very easy to customize fixtures and produce custom made fixtures very, very cheaply as one-offs to do work holding applications to hold pieces of complex and organic shapes. So it's just interesting to see how this part that we're looking at on the screen, none of it was additively manufactured, but the tooling to make it and the manufacturing processes all relied quite heavily on additive manufacturing as a whole. So to say, short and sweet, thank you very much for taking the time. I am really excited to be part of this. I think there's lots and lots of very interesting people on this, and yeah, I'm very much looking forward to being able to work with some of you guys.